everybody, this is our 2,3 biphosphoglycerate shunt video. So this video is talking about a shunt off of glycolysis, specifically one that happens in red blood cells called the 2,3 biphosphoglycerate shunt. Now 2,3 biphosphoglycerate can also be called 2,3 diphosphoglycerate, just, keeping in the trend of calling things by multiple names, but bi and di both mean, two phosphates on the molecule. Now, why this shunt is important and why it happens in red blood cells is that it has a lot to do with hemoglobin's affinity for oxygen. If you think back to AMP2 and you think of hemoglobins, so hemoglobin is HB. And it has an affinity for oxygen, and what that means is how strongly the hemoglobin binds the oxygen. And remember that hemoglobin is responsible for carrying oxygen to tissues, so carrying oxygen through the blood. It binds the oxygen in your pulmonary capillaries, so where you're breathing and getting the oxygen from the air that you're breathing in. And it releases the oxygen in the tissue capillaries so that the cells of the tissue can use that oxygen. So they can take up the oxygen and use it for their electron transport chains. Now the affinity of the hemoglobin for oxygen is going to determine whether it's binding that oxygen or whether it's letting go. So hemoglobin with a high affinity for oxygen is going to bind the oxygen and it'll hold on to it pretty tightly. When you reduce that affinity, so hemoglobin with a low affinity for oxygen doesn't bind, it releases, or lets go of the oxygen. So what you want is to have in your pulmonary capillaries, you want to have a high affinity here so that you can bind the oxygen onto the hemoglobin, and then when you get into the capillaries of the tissue, you want to have a low affinity so that you can let go of the oxygen. Now various things affect the affinity of hemoglobin for oxygen, so things like 2,3 biphosphoglycerate that reduces affinity. The Bohr effect reduces the affinity. This is when you have an exercising tissue and you have hyperlactemia, so like a lactic acid situation going on, so you have a low pH. That's the Bohr effect. It reduces the affinity, and if you think about that, it makes sense. If you have an exercising tissue, it needs oxygen, and it's essentially signaling with that lactic acid to the hemoglobin, let go of that oxygen, let me have more oxygen. PO2 changes affinity. So high PO2, so meaning a lot of oxygen present, increases the affinity. Low PO2 decreases the affinity. Things like that. We don't need to get all into all that. What we are looking at specifically is our biphosphoglycerate in our red blood cells and how it's going to reduce the affinity of hemoglobin. So it's going to make the hemoglobin let go of oxygen. Now, something like the Bohr effect, this is, acid. Acid, low pH, acidity is going to be something that happens very quickly. 2,3-biphosphoglycerate is more of a slower thing, a longer lasting, but slower acting kind of thing. So they work in this, kind of the same way that they are making hemoglobin let go of oxygen, but they, one is fast and quick, over quickly, and the other is, slow and lasts a long time. Now, 2,3-biphosphoglycerate is something called an allosteric effector. What that means, when something is allosteric, it changes the shape of something. So when something binds to another something, it changes the actual shape of it. The conformation of the molecule is actually changed. So when you change the shape of a molecule, you change its function. And in the case of hemoglobin, when you change the shape of it, you change its affinity for oxygen. So when 2,3-biphosphoglycerate binds to hemoglobin, it changes the shape and makes it hold on less tightly to oxygen. Okay, so for here, we want to go back to our glycolysis metabolic map. Just for a second, we don't need to get into a lot of detail. I just kind of wrote out the pertinent parts here of glycolysis so that we can see where the shunt is. So we'll start here at glyceraldehyde 3-phosphate. So this isn't the beginning, but this is just the step before we can branch off into our 2,3-biphospho, I don't know why I wrote that way, biphosphoglycerate shunt over here. So here's our main glycolysis pathway. So glyceraldehyde 3-phosphate goes into 1,3-biphosphoglycerate, goes into phosphoglycerate, goes into 2-phosphoglycerate, then phosphoenol pyruvate, and then pyruvate, which then acetyl-CoA and into the Krebs cycle. But we're not super worried about that. We are just thinking about right here where 1,3-biphosphoglycerate can take this shunt and go into the 2,3-biphosphoglycerate shunt. Now, things will happen. We will create our 2,3-biphosphoglycerate, and then we will return to the main glycolysis pathway. Reasons for this: we're in a red blood cell. We want to be able to do this so that we can, handle our hemoglobin and its affinity for oxygen. But red blood cells don't have mitochondria. They have to do glycolysis for energy. So we don't want to just have this be kind of a shunt that is an end in itself. We do ideally want to return to glycolysis so we can go back and get our energy. So we're not going to go into acetyl-CoA in the Krebs cycle like we normally would. We're just going to get 2 ATP, and the red blood cell is just going to have to be happy with that because it doesn't have any mitochondria. So this shunt is allowing us to handle the hemoglobin situation, to make the hemoglobin let go of the oxygen, but then also allowing us to continue back on into our glycolysis to make energy so that those red blood cells don't essentially have to choose between having this 2,3-biphosphoglycerate to make the hemoglobin let go of the oxygen and creating energy. They don't have to decide which one they're going to do. They don't have to do either or. They can do both. So that's why it returns to the glycolysis pathway. Okay, so here is our reaction going on here. So we're starting with our glyceraldehyde 3-phosphate. So here we have, two of them because remember glycolysis will be happening twice essentially, but we can just look at it as one time. So our glyceraldehyde 3-phosphate is acted on by this enzyme, glyceraldehyde 3-phosphate dehydrogenase. Notice again, dehydrogenase, we're going to be taking a hydrogen off of something, in this case glyceraldehyde 3-phosphate. So it's a really simple way of naming enzymes. It tells you exactly what the enzyme is going to do. So here we're going to be creating, taking NAD and taking that hydrogen and adding NAD, or creating NADH with hydrogens added to the NAD, something we've seen a zillion times before. Then we are using that to create 1,3-biphosphoglycerate. Okay, so this is where we are here. So we're looking at this step right here, and we're getting our 1,3-biphosphoglycerate. Okay, so that's this molecule here. So this is our part of glycolysis where we are going to branch off. Okay, so here we have kind of a truncated glycolysis metabolic map where, okay, so it goes straight from glucose, it kind of skips over some steps, goes right into 1,3-biphosphoglycerate. So let's try and get these side by side here. So see, 1,3-biphosphoglycerate. We'll have our shunt over here. Then we will rejoin at 3-phosphoglycerate. And then yada yada yada, we get to our pyruvate at the end where we get our ATP. Because we don't have mitochondria, so we're not going to do the electron transport chain, we get lactic acid, which we can deal with in the Cori cycle because we're not having a hypoxic situation. Anyway, we're not going to worry about that lactic acid or the pyruvate. We're just worried about right here and our little 2,3-biphosphoglycerate shunt. Another name for our 2,3-biphosphoglycerate shunt is the Rappaport-Lubering shunt, named after the scientists who discovered it or described it first. And here it is. It is a very simple shunt. There is not a lot going on. It's just rearranging phosphate. Instead of being on the first carbon and the third carbon for 1,3-biphosphoglycerate. So if we look at the molecule, there's a phosphate, there's a phosphate. Now we're putting it on 2,3, the second carbon and the third carbon. So instead of 1,3, we're putting it on 2 and 3. So just essentially shifting the phosphate from here to here. That's it. And this is what can bind to hemoglobin. Changes the shape, so causes a conformational change in the hemoglobin. And that makes it have lower affinity for oxygen. So it lets go of the oxygen. So this is important. We're going to take our oxyhemoglobin, so HbO2 is oxyhemoglobin, that's hemoglobin with oxygen bound to it. We put the 2,3-biphosphoglycerate onto it, it binds to it, changes the shape, so our hemoglobin now has the 2,3-biphosphoglycerate on it, and it has let go of an oxygen, and it's called deoxyhemoglobin. So we've let go of our oxygen. The oxygen can diffuse out into the blood, into the tissues, and into the cells. Okay, now we've done what we needed to do, so we just kind of take the phosphate away here, and we have just 3-phosphoglycerate. So we take away this phosphate, the 2-phosphate. We're left with just this 1-phosphate on the 3 carbon, on the third carbon, and that gives us 3-phosphoglycerate. We are back in our glycolysis here. Okay. So if you notice just a little pattern here, these numbers before are saying which carbons the substances, the whatever the molecule is here, we're talking about phosphate. So on this molecule, the phosphates are on the 1 carbon and the 3 carbon. On this molecule, the phosphates are on the 2 carbon and the 3 carbon. This is biphosphoglycerate, both of these, 2 phosphates. This, not biphospho anything, it's just plain old phosphoglycerate, so it's just 1 phosphate. We lost 1. Where is that 1? It's on the 3rd carbon. Then here, this is 2 phosphoglycerate. Well, now it's on the 2nd carbon. So the names of the molecules are just kind of describing where those phosphates are at this point. Okay, so what is going to affect our 2,3-biphosphoglycerate concentration in our red blood cells? 1, being a fetus. If you are a fetus, your hemoglobin needs to have a lower affinity for 2,3-biphosphoglycerate, because being a fetus, you have to have a higher affinity for oxygen. And the reason for this is that the blood coming from the mother to the fetus is not got that much oxygen. It has a lot, but not a super high amount of oxygen. So the fetus really needs to be able to grab hold of that oxygen so that it can have the amount of oxygen that it needs in order to, live. So the fetal hemoglobin has to have a higher affinity for oxygen than the mother's hemoglobin. And so fetal hemoglobin is not really friends with 2,3-biphosphoglycerate. You don't have a real need for 2,3-biphosphoglycerate as a fetus. Your main goal is just to get the oxygen in the first place, so you won't be binding this quite so much to your hemoglobin, which prevents the 2,3-biphosphoglycerate from knocking the oxygen off the hemoglobin. Now, assuming you are not a fetus and you are an adult person moving around in the world, if you have a low PO2, this will cause you to have higher concentrations of biphosphoglycerate. So not having a lot of oxygen in your blood, so you're sitting there in a hypoxic situation, your cells are needing the oxygen, you want to let go of whatever oxygen you have on your hemoglobin so that the cells can have it. If you get blood from a transfusion, when blood is stored, it tends to lose 2,3-biphosphoglycerate. Now, recently, I don't remember what year, or it's quite recent that they discovered ways of adding things to stored blood that prevents that from happening for this very reason, just so that you don't decrease your 2,3-biphosphoglycerate concentration. Because if you think about it, you get a big old transfusion without hardly any biphosphoglycerate, and suddenly your hemoglobin has too high of an affinity for oxygen and you can't let go of that oxygen for your cells, you can have trouble. So they add things to the stored blood to prevent that from happening. Now, deficiency of glycolytic enzymes. What that means are enzymes for glycolysis. Okay, so let's think back to glycolysis. We don't need the whole map here. We can just look at our little abbreviated map that I wrote out here. Remember that we have our thing that we're looking at here. So this is our shunt that happens here. Anything before that is considered proximal to it, and anything after that is considered distal to it. So if we're thinking about what might affect our concentrations of biphosphoglycerate, anything that goes wrong with glycolysis proximal to the shunt can affect the concentration here. So if we are lacking the enzyme that converts glyceraldehyde into 1,3-biphosphoglycerate, well then, if we don't have 1,3-biphosphoglycerate, we're going to have a hard time getting 2,3-biphosphoglycerate. That would be a problem. Anything proximal, any problems proximal, would be a problem. Distal wouldn't have any effect on this. Once we've re-entered glycolysis, this has done its job. This is over with. It's done. So if we have any trouble with any of these enzymes, distal to it, well, that gives us a problem with creating our ATP. That's another story. But it doesn't give us any trouble with our 2,3-biphosphoglycerate concentrations. So proximal deficiencies of our glycolytic enzymes would be bad for 2,3-biphosphoglycerate. Distal deficiencies of our glycolytic enzymes would have no effect at all on the biphosphoglycerate, would have effect on ATP though. And then here, hypophosphatemia, this means not having enough phosphate in the blood. That would decrease our concentration of 2,3-biphosphoglycerate. This is a molecule that contains phosphate. So is this. So are these. If you don't have phosphate, you're going to have less of these, just generally speaking. So those are the things that could affect your concentrations for there. In our next video, we will go into another shunt off of glycolysis, which is the pentose phosphate pathway.